So it kind of goes back and forth. But I do want you to think about one thing, is that they didn't crash test cars back in the day 50 years ago the same way they do now. So now you can go on and check your rating on your car, and if you have a horrible crash test, you're probably not going to buy that car. So I'll kind of give you a hint. It's going to be the 2009 Chevy that's going to be safer, and take a look why. So the only thing with this video, the cars are painted different colors. The colors don't really affect the crash safety of the car, so don't worry about that. And they are ruining a really classic 1959 Chevy Bel Air. It always surprises me because that's 35 miles per hour, I think, or maybe 40, but 35, 40 miles per hour doesn't seem very fast when you're driving it on the streets. Again, it's tough to tell who would be safer, so they're going to eventually go inside the cars here with the cameras. And some people will note that seatbelts were not required in cars in the 1950s. So you're going to see that the passenger with the red hat there is going to go flying forward according to Newton's first law, and the windshield in that car, you can see at the top, actually gets ejected. All right, so here's inside the 1959, the older car, classic car, and that's at 35 miles per hour. No seatbelt, no airbag. And you can see both fronts of the cars crumble a lot. Again, there's the windshield. That's just crazy to me, like windshield goes flying forward. Inside the new car here with airbag and seatbelt. And you can see that'd be a survivable crash. They paint the dummy's face so you can make sure where it's hitting inside the car, and you can make sure the force is distributed evenly over the face. And I just want to pause it here if I can. Notice this crumples on purpose because they want the force to be distributed, and they want that to crush over time. So the force basically gets spread out over a longer time. It's kind of like if you jumped off a step as a kid, you want to kind of bend your knees as you hit the ground to dissipate the force over a longer time, so the force gets reduced. So this car actually looks pretty good. The front's crushed. That's the crumple zone that was designed by the engineers. The safety cage is over here, and that has not been, there's no intrusion into that. Let's look at the old car, and we're going to see how the old car did compared to the 2009. Oh, sorry, they show us one more angle here. You can see the passenger looks pretty okay. Yeah, that's the front of the old car looking at us. That's not a good sign. And you can see the safety cage. Well, they didn't have one, but all this metal just got jammed into the passenger compartment. So which one's safer, old car, new car? It is the new car, which makes sense in a way because 50 years of technology and crash tests, hopefully things have improved. All right, we'll finish with this momentum and impulse summary. 2 mathematical takeaways. What's the momentum equation? You should have jotted down this right here. And then secondly, what's the impulse equation? You should have jotted down this right here. Momentum and impulse is so cool because if you play a sport, if you drive a car, anything when you're physically moving, these equations basically describe what you see every day. And so I remember being a high school student learning about momentum, and then even like going out to play baseball or play basketball, it just starts to make a lot of sense as why you see the things you do in life. So, all right, so last time we introduced momentum and impulse. So take a moment just to do a momentum warm-up, see what you remember, and then when you're ready, go ahead and hit play here. All right, what's momentum? We said last time that Newton says to have momentum, you need 2 things. You need to have a mass, and it has to have a velocity to it. So if you just have mass, you have inertia. But if you have mass and motion, that's momentum. A little confusing, we pointed out last time, is that momentum is represented by the letter P, because we're kind of running out of variables, and then the units for momentum are kilogram meters per second. Give an example of something that has momentum. I thought to myself, the most common incorrect answer is somebody says, oh, a rock has momentum. And I'd say, no, we'd say a rock has a lot of momentum, so a rock has a lot of inertia, but the rock doesn't have momentum until it's rolling. So if you picture like a big rock rolling down a hill, that has a lot of momentum. It also has a lot of inertia because it has lots of mass. And then right before we left last time, we talked about what an impulse was. So another term that Newton says is very helpful to talk about is that if you push on something, a force exerted on that something for a certain amount of time, you exert an impulse onto that object. And impulses have the ability to change an object's momentum. So if you have something at rest, like say you're making a snowman as a kid and you're rolling that ball, for example, the snowball, when it's at rest, it has no momentum. If you want it to get momentum, you got to push on it with a certain force for a certain amount of time. Okay, let's take these equations for a spin. It says a train car with mass 650,000 kilograms travels with a velocity of 30 meters per second, which is about 60 miles per hour. Number one, what's the momentum of this train car? And notice it's the train car, it's not the whole train. So now picture, I don't know how long a train is, but it's at least probably 20 cars long. So trains have a lot of mass, and that means they're going to have a lot of momentum. So number one, figure out the momentum of that train car. Number two, at what velocity would a 0.145 kilogram baseball, that's the actual mass of the baseball, I looked it up on the Google and MLB.com, I believe it was, Major League Baseball. How fast would a baseball, like this one right here, have to travel in order to cancel the train's momentum? So maybe, and never throw a baseball at a train. Bad idea. You get a lot of trouble, probably arrested. But say that you had a train coming, and you're like, theoretically, there should be some speed at which this ball could be projected. So what would that speed be? So go ahead and hit pause. Try this one out and see what you come up with. All right, so looks like quite a bit of work here. Let me grab my pen here. Let's go. And let's go right with this one. Momentum of the train. So givens. M of the train, so you see M sub t is 650,000 kilograms. Velocity of the train is 30 meters per second. And don't look over here just yet because that's for part two. But we're looking for the momentum P of the train. So the only equation we have for momentum is P equals mv. So let's write it right here, P equals mv. And so the momentum of the train is equal to the mass of the train times velocity. You multiply this big number times this number, and you get that the train has a momentum of 19,500,000 kilogram meters per second. So that's the momentum of one train car, and that's a large momentum. And the singular of momentum is momenta, in case anybody ever says it like that. But so the momentum of that train car is 19,500,000. Well, the second part of this question says at what velocity would a baseball have to have in order to cancel the train's momentum, such that maybe in your mind you're picturing you throw it off the train and it cancels off the momentum, and then all of a sudden the train stops. Well, to do this, I wrote down that the mass of the ball is 0.145 kilograms, and I'm going to say as we know that this train's momentum is going this way because that's the direction of the velocity, and you're going to throw the ball this way. And so I'm just going to say the momentum of the ball has to be the same as the train, but basically it's in the opposite direction. So I just said, okay, 19,500,000, that's the momentum of our ball now. And I come down here, and the velocity of the ball, if we use our algebra triangle from last time, is just going to be our momentum of the ball divided by the mass. So it's 19,500,000 divided by 0.145. And when you look at that, the velocity of the ball comes out to be this number right here, which is 134 million meters per second. And I converted that to miles per hour just to kind of show you how big it is. It's roughly 299 million miles per hour, or if you round it off, it's 300 million miles per hour. So you would have to throw that ball at 300 million miles per hour. And just for like a reference, it's about half the speed of light you'd have to throw that ball. You would throw the ball, I did this calculation because I kind of nerded out on this calculation, but you would throw the ball so fast, in fact, that in 1 second, it could circle the earth 3 times. So you might ask yourself, why do you have to throw the ball so fast in order to cancel off the momentum of the train? Well, it's because the mass of the train is just so big compared to the mass of the ball. So that's why you see these big NFL players and they're so massive and they hit somebody and that person they hit goes flying. It's because that massive object person has a lot of momentum just by virtue of it being massive. All right, so stay away from trains when they're moving. All right, impulse example. A ball is hit with a force of 500 newtons. Kind of with the baseball theme here, I like it. The time that the bat is in contact with the ball is 0.5 seconds. What is the impulse delivered to the ball? So as always, go ahead and hit pause, try this one out, and when you think you got a good, reasonable guess, come on back. It's not a bad calculation whatsoever. So we got our force is 500 newtons, our time is 0.5 seconds. We're doing our physics format even on the easy ones because then the easy ones get even easier. You're looking for impulse. You only have one impulse equation. It says that I equals F times T. So you just multiply 500 newtons times 0.5 seconds. And you get the 250 newton seconds of impulse. So that is not a bad calculation. One thing to point out, if you do play sports and you've ever had a coach yell at you to follow through, the reason they yell at you to follow through is not because you can get more force on whatever you're hitting. It's because if you increase your time, for example, say you're throwing a ball, and if you can just get a split second more time of you touching the ball, then that's going to affect the impulse that you deliver to the ball, which means that ball is going to be going faster. So let's say, for example, if you could double your time of contact while we're hitting this ball, then you're actually going to double the impulse up to 500 Newton seconds. So the concept of follow through, whether it's hitting a volleyball, playing lacrosse, hockey, whatever it is, following through in sports, basketball, and you're shooting a free throw is hugely important. All right, this is kind of the big concept for today. Is it possible to change an object's momentum? And we said this last time, we've said it a couple times, but yes, absolutely it is. Isaac Newton said you could change an object's momentum by having a force act on that, whatever it is, for a certain amount of time. So again, I have my glass of water at my desk. It's not moving, but if I want to change its momentum, right now it has 0. I just push or pull it with a force for a certain amount of time. And Isaac Newton said that's an impulse. So somebody out there might be wondering, well, it seems like you're just making these terms up. Where did it come from? And I actually find this super fascinating. Maybe that's why I'm a physics teacher. But this is how he came up with this idea. And it's a little bit of math, but it's actually not too bad. What Newton does is he says his second law is that force is equal to mass times acceleration. And so he says, okay, F equals ma. And then he started thinking about, well, what's acceleration really mean? The definition of acceleration is that you take your final velocity, or VF, minus your initial velocity, VI. And before we didn't use F's and I's, we just use V and VO. But just to kind of show that it's final velocity, I'm going to label it VF, final minus initial velocity. And then if you take your final time minus your initial time, you're going to get your change in time. So basically it says you take your final velocity minus your initial, divide it by your final time minus initial. And he said, well, this quantity on top, we could just call that's your change in velocity. That's how much your velocity changes. And a lot of times when we're doing these problems, there weren't cars around in Newton's time, but you can think about a car example is a lot of times your car is starting from time equals 0. So your initial time is 0. Well, let's just put a t down here then, because this time, if it's 0, is just going to go away, right? So t final we can just call t. So Newton says, okay, your change in velocity over time is equal to your acceleration. So like a car manufacturer says you go 0 to 60 miles per hour in 4 seconds. They're describing the acceleration. So what we're going to do is we're going to say, hey, a is equal to your change in v over t. So where there's an a here, we're just going to rewrite it as change in v over t. Okay, and then just because we can, algebra says that we can multiply both sides by time. So let's just multiply both sides by time. So you can see, and sorry, it's kind of bad handwriting, but I just multiplied both sides, the right side by time, the left side. Well, if you do that on this side, since there's a time on the bottom, it cancels. So Newton comes up with this new equation, and it seems important because I quadruple start it, but it says if you have force times time is equal to an object's mass times the change in velocity. Well, Newton, what he says is, he said, let's call force times time, that's what's called an impulse. Okay, so force times time, he just says, let's call it impulse. And if you have a force acting over a time, it's going to act on a mass. And if it acts on a mass, it's going to change that mass's velocity. So if you think about this, anytime you've ever pushed on something for a certain amount of time, on a mass, it's going to change its velocity. We're going to take it one step further.